So we've got a 2-liter, 2,000 cubic centimeter oil can that's in the shape of a cylinder. And we want to know what dimensions will use the least amount of material. So what do we need to do?
Optimize.
Right, so what do we need to do to optimize?
We want to minimize surface area.
All right, we want to minimize surface area, right? Dimensions to use the least amount of material, so we need to write an equation for the surface area. I'm just going to call it A. Surface area should be what? For a cylinder, it should be 2 pi r squareds, right? One for the top and one for the bottom. And then what's the lateral surface area of a cylinder?
Two pi times the height.
2 pi r, right? Circumference times the height. And so the issue that we come across here is what? We've got what going on here in our surface area equation?
There are 2 variables.
2 variables, which means we got to find a way to relate the 2 variables so that we can cancel one of them out and write it in terms of the other one. So we're designing a 2-liter, 2,000 cubic centimeter oil can, which means that the volume must be 2,000. And what's the volume of a cylinder?
Pi r squared h.
Pi r squared h, which tells us that h is 2,000 over pi r squared. So that means we can just take a 2,000 over pi r squared, replace the h with it, and we end up with area is 2 pi r squared plus 2 pi r times that 2,000 over the pi r squared. Good or no? All right, cancel out the pi's, and we now got surface area is 2 pi r squared plus 4,000, and then r over r squared is over r, or r to the negative 1. And now we're ready to do our optimization, right? We're ready to take our derivative and figure out when this is at a minimum. So we'll say a prime should be 4 pi r, and then minus 4,000 r to the negative 2, or 4,000 over r squared, which gives us 4 pi r cubed minus 4,000 over r squared if we write it all with one common denominator. Good or no?
Splendid.
Great. All right. So we know that this is undefined if r equals 0, but that doesn't really make any sort of sense. We're not going to have a cylinder with a radius of 0, so we'll ignore that. And this equals 0 when 4 pi r cubed minus 4,000 equals 0, which would be r is equal to, well, we'll add the 4,000, divide by 4 gives you 1,000, and divide by the pi, we got 1,000 over pi. And cube root that ought to be 10 over the cube root of pi. It looks like, what were our units? Centimeters. And we'll have to do what with that? We'll have to prove that that is a minimum, right?
Indeed.
So let's make a sign chart with that. There's 10 over the cube root of pi. And if we plug in something, let's see, more than 0, but less than 10 over the cube root of pi, all right, it's not f prime, it's a prime, right? Into our derivative, something like 1, let's say. Plug in 1 here, you got 4 pi minus 4,000, which is a negative, over a positive, so you end up with a negative. So we're decreasing. And plug in something more than this, like let's say 10. We plug in 10, we got 4,000 pi minus 4,000, definitely positive over a positive, so increasing. Okay, so we definitely have a minimum with an r equal to 10 over the cube root of pi. And I don't know, it asks probably for the dimensions that use the least material, so we'd also have to find the height. So height would be 2,000 over pi times that radius squared, which should simplify out pretty easily also, right? This is 2,000 over 100, right? 10 squared is your 100, so that should just give us 20 in the numerator. And then we've got pi over pi to the 2/3. So pi over pi to the 2/3 is pi to the 1/3. So radius of 10 over the cube root of pi with a height of 20 over the cube root of pi. Good or no?
So good.
Wonderful. All right, let's do another one. So we are going to inscribe a cylinder into a sphere. So let's draw a picture. Wow, those dotted lines are not very good, are they? There we go. There's our sphere. And here is our, I don't like how I did that. I don't like that either. There we go. There's our cylinder inscribed in our sphere. And we know the only thing we really are given here is that the sphere has a radius of 10. That's really all that we're given. So what can we do from there to find the max volume of the cylinder? What do we first probably need? We probably need an equation that represents the volume. And what's the volume of a cylinder?
R squared H.
By r squared h. And once again, we come across the same problem that we had in the last one, that we've got two different variables, so we have to find a way to relate them to each other. And so how are we going to do that? Let's label what our r is. So like here's the radius of the cylinder, right? And here's our height of our cylinder. Just draw it over here just because that'll make it a little easier. How can we relate those things together?
Do we make a triangle?
Sure.
Like, so that the hypotenuse of the triangle is the radius? And
Okay,
then
so radius of the sphere?
the radius of the sphere. And it goes to like the corner, yeah, right there.
Like that. Okay, like that kind of triangle. Sure, we can do that. So what is this side length here? The side length is h over 2. And what is the hypotenuse? It is 10, right? And so we should be able to use the Pythagorean theorem here to tell us that h squared over 4 plus r squared is equal to 100. And what do we want to replace? Do you want to replace the r's or the h's?
Replace the H's.
Really? I don't want to do
Or
that.
like,
I'd much rather replace the r's
okay,
just because I've got r squared and I've got r squared. So I could just find out what r squared is and replace it. So I'm going to say r squared is 100 minus h squared over 4. You could do it the other way, but this is going to make, I think, our lives a little bit easier. We got pi h times 100 minus h squared over 4. Or 100 pi h minus pi h cubed over 4. Good or no?
Good.
And what's v prime? Hundred pi, right? Minus 3 pi h squared over 4. And we want to know, when does that equal 0? When does that equal 0? We got 3 pi h squared over 4 equals 100 pi. Pi's will cancel, right? We end up with h squared equals 400 over 3, or 20 over root 3, plus or minus 20 over root 3, but we can probably ignore the minus 20 over root 3 as a height. Good or no? Everyone all right with that or not?
All good.
Yeah, it's good.
Yes.
Okay. Now plug in something between 0 and 20 over root 3, like 1 to our derivative. That gives us 100 pi minus 3 pi over 4. That's definitely positive, so we're going up. And then something more than 20 over root 3, like 19 or something like that. Definitely this is going to be much bigger than this is, right? When we square 19, 19 squared is going to be pretty big, right? So we're going to get a minus there. And we clearly have a max at height equals 20 over root 3. And if height is 20 over root 3, we should be able to plug that in to find our volume. And I'm not going to bother to evaluate it out, but we get the idea, right? Or no?
Yes.
Cool. All right, let's do one more of these nice, fun optimizations. In fact, why don't you guys do this optimization problem on your own? I'll give you about 5-6 minutes here and you can work through it. Sound good? Ready, go. So first off, we've got a cylinder and it's open at the top. So we know that it's only going to have one base to it, if we have to deal with that at all. And then we know it's going to have a capacity of 24 pi cubic inches. So that's our volume. And we've got assorted different costs for the material for the bottom and for the curved parts on the side. So we want to minimize the cost. So the cost should be the cost for the base, which is 15 cents per square inch. So 15. And what is the area? How many square inches do we have on the bottom? We have pi times the radius squared, right? That's just the base. And then we have 5 inches for the lateral area part, which is 2 pi r h. And so once again, we've got the same issue, which is that we have multiple variables. So we go in and we say, well, volume, which is pi r squared h, is 24 pi. Or h, seems like h would be the better one to eliminate since we got one h and an r squared and an r. H is equal to 24 over r squared. Everybody good with that so far? So we got 10 pi r and then times h, 24 over r squared. Or a final cost equation of cost is 15 pi r squared plus, what does that become? 240 pi r to the negative 1. Good or no?
Yeah.
Okay, we'll take our derivative, c prime, should be 30 pi r, and then minus 240 pi r to the negative 2. Or if we get a common denominator, 30 pi r cubed minus 240 pi over r squared. And just like the one previously, it's only undefined if r is 0, but r equals 0 doesn't make a lot of sense, right? We're not going to have a cylinder with a radius of 0, although the cost of making that cylinder would be 0 since it doesn't exist. We actually want to have a cylinder. So let's set this equal to 0. That tells us that, so a new page where we got a little more room. We got 30 pi r cubed equals 240 pi. So we'll cancel the pi's, divide, we got r cubed equals 8, or r equals 2. I think it was what, 2 inches? Yep, 2 inches. And we'll make our sign chart here. Put something in between 0 and 2, like 1 to our derivative. Plug in a 1, the denominator is going to be positive, and the numerator is going to be 30 pi minus 240 pi, which is negative, so we should be decreasing. And then greater than 2, like let's say 3, this ought to be 27 times 30, which ought to be 810 pi minus 240 pi, which is definitely positive. So we have a minimum cost when r is 2 inches. And I think it asked for the dimensions, right? So we could go back in and say the height is 24 over r squared, which is 6 inches. Good or no? Any issues with that? All right, if there's no issues, let's start talking about related rates. Just do a few of these, and then you'll be ready to do all of the fun and exciting problems on those 2 pages that I posted the other day. So for our related rate problems, a couple of things to just keep in mind. First, figure out what variable you're looking for the rate of change of. Okay. And most importantly, for all these related rate problems, draw yourself a picture and label the important things. And remember that when you label for a related rate problem, don't label anything that is changing. Okay. You can put variables in for the things that are changing, but if it says that the angle is changing at some rate, what is the velocity when the angle is 7? Well, don't put a 7 for the angle, put a theta for the angle. If the quantity is changing, put a variable for it. If the quantity is not changing, then you can label it. Good?
Yeah.
Okay. So that's really important. Otherwise, that ends up screwing people up all the time. So then once you've got your picture all drawn, then you just write yourself an equation that somehow has in the variable that you're looking for the rate of change of in it. And you differentiate both sides of your equation with respect to time. So remember that you're using the chain rule, implicit differentiation, if you're differentiating something that's not a t with respect to t, and then plug stuff in and get an answer. Sound good? So what we're looking for is, in a related rate problem, is how is one quantity changing with respect to time in relation to how some other quantities in the problem are changing. So let's start with a nice easy one. We've got a hot air balloon rising straight up from a level field. Oh, let's draw green. There's the nice green field. Look at that. And we'll have a red hot air balloon. Look at that. And it's going up. And here we are over here. We are blue, tracking this hot air balloon as it rises. Okay. Looking at the angle. So this is the situation we're sitting here looking at. We've got a hot air balloon rising up. We're standing away on a level field looking at it. We're tracking the angle, and we're going to use that to determine how fast the balloon itself is rising. So first off, the balloon is rising straight up. So what does that tell us about this angle here?
90 degrees.
And is that angle changing?
No.
No. So we can label that as a constant quantity. All right. What else? Let's see. What about the green line for our field? How far away are we from where the balloon lifted off?
500 feet.
500 feet. Is that distance from the liftoff point to our location changing?
No.
Nope. Exactly. So 500. All right. What else is important in here? Let's see. We're looking at the angle of elevation from the tracker to the balloon, and we're saying it's pi over 4, and it's increasing at 0.14 radians per minute. That would be this angle right here, right? So at the point that we're interested in, what is that angle?
Pi over 4 radians.
Yeah, it's pi over 4 radians. But is it changing?
Yes.
Yes. So we can't label it as pi over 4. We'll just label it as theta. And the theta value that we're interested in, we can write this off to the side, is theta equals pi over 4. And we're also given a value for how theta is changing, d theta dt. And d theta dt is increasing, so that rate of change should be positive, of 0.14 radians per minute. So far, good? With our nice little picture here?
It's quite nice.
Yes, isn't it? Okay. So we want to know how fast is the balloon rising. That'd be this rate of change, right? We want to know how quickly it's going up. What is the rate of change of this height? So let's label the height. Do we know the height?
No, but we can find it out.
We could find it out. Is that height changing?
Yes.
Yes.
Yes. So we probably don't want to label it with a number. We want to label it with a variable. Since this is going in a y direction, how about y? That'd be okay with everybody? And we want to know, how is y changing? What is dy dt? How is y changing with respect to time? That's what we're looking for. So we need to write an equation to relate the things that we have in the problem, and that we can solve hopefully for dy dt by taking a derivative with respect to t. So we're given y, 500, a right angle, and some other angle theta on this triangle. How can we relate all this junk here together?
We could write an equation relating h to theta, maybe.
You mean y?
Y.
I don't have an h. Maybe you have an h, but I don't.
I just put h and then
That's
you put,
fine.
I'm not,
Yeah, so what can that equation look like? Yeah, so Ryan, you put that in the chat there. It's tangent, right? Tangent of theta ought to equal opposite over adjacent, right? So that if we want to make this even a little bit easier to look at, how about 500 tangent theta equals y? And then now, if we were to take the derivative of both sides of this with respect to t, that would give us 500 secant squared theta d theta dt equals dy dt. And all we need to do then is plug in our theta value and find the secant squared of that, and plug in our d theta dt value and multiply them all together and by 500, and we should get our answer. Good or no?
Great.
Cool. So we have secant of pi over 4. What's the secant of pi over 4?
Root 2.
Root 2. Secant squared then ought to be 2. So what do we got? We got 1,000 times 0.14, which ought to be
140.
140 feet per minute. Good or no?
That was great.
Any issues with that?
No.
All right, let's do another one. Got a police car approaching a right-angled intersection from the north. Got a car that has turned the corner and is moving east, and then a bunch of numbers. So let's sort of draw this situation out. We got a car approaching it from the north, and another car that's turned the corner and is going east. We're talking about when the police car is 0.6 miles north of the intersection. Is that distance changing?
Yeah.
Yeah, and we got the car is 0.8 miles to the east. Is that distance changing?
Also, yeah.
Yeah, so we don't want to label those with numbers yet, but we could label them with variables. How about y and x? And then we're also talking about the distance between the two cars. So if this is my police car and this is my criminal or whatever, I guess it's a speeding car, sort of a criminal. Not as bad as it could be though. The distance between them would be this. Is that distance changing as x and y change? Should be. We'll call that one z, right? And we know that at the point we're interested in, x is 0.8 and y is 0.6. And it doesn't give us z, right, for that, but we could figure it out in a bit probably because we know this is a right-angled intersection, which is not changing. And we know the distance between the cars, dz dt, is what? Changing at what rate? It's
20 miles per hour.
increasing at 20 miles an hour. And we know that the police car is moving at 60 miles an hour. That'd be a rate of change of x. Sorry, a rate of change of y. Looking at the wrong one. dy dt. And the police car is moving at 60 miles an hour. So what should the dy dt be?
Probably 60.
Mm,
You could maybe say negative 60 since it's moving down.
negative 60, because we have to think this y distance is decreasing, right? This value is getting smaller. And so our rate of change of y has to be a negative. Anytime the rate of change of something, or anytime something is decreasing, its rate of change has to be negative. And anytime something is increasing, like the distance between them, right, that tells us that our rate of change needs to be positive. So now, how do we relate x, y, and z to figure out the speed of the speeding car, dx dt?
Pythagorean theorem.
Pythagorean theorem. So x squared plus y squared equals z squared. And we got a couple of different options here. But probably the quickest and easiest one is just to take the derivative with respect to t. 2x dx dt plus 2y dy dt equals 2z dz dt. And I have x, and I'm looking for dx dt, and I have y, and I have dy dt, and I have dz dt, but I'm missing z. So to find z, we'll just take those values and plug them into the Pythagorean theorem to give us z equals what?
1.
Z equals 1. So we'll now plug all that stuff in. 2 times x ought to be 2 times 0.8 or 1.6 times dx dt, which is what we're looking for, plus 2 times y, which ought to be 1.2 times negative 60. So 1.2 times negative 60 equals 2z dz dt. So that'd be 2 times 1 is 2 times 20 is 40. And we're just looking for dx dt. So dx dt, and what do we get here? 1.2 times negative 60 is negative 72. So negative 72 plus 40 ought to be 112 divided by 1.6, which should be, I believe, 70 miles an hour. Good or no?
Good.
Any questions, any issues there?
So this car is barely speeding.
I mean,
It could be a residential
I don't
area.
recall any information in here about the speed limit. So
That's true. And I guess the fact that there's a right angle would imply that we're not on the freeway.
probably not. There are usually not right angles on the freeway.
That would not be safe.
Yes, if you are turning at a right angle on the freeway, you are making a poor life choice. So I recommend against making right angle turns on the freeway.
All right, cool. I won't
Yeah.
do that.
Look at this, math and life advice. It's wonderful. All right, everybody feel okay about that? Let's do one more and then we'll call it a day. You guys want to try and work through this one on your own?
Yes, please.
All right, I'll give you about 5 or 6 minutes here and then we'll go back through it. Ready, go. So we got water flowing into a conical tank that is got the point down. It has a height of 10 feet. Is the height of the tank itself changing?
No, it is not.
Nope. So we can call that 10 if we wish. And it has a radius of 5, which is also not changing for the tank itself. And then we want to know how fast is the water level rising when the water is 6 feet deep. So the water as it rises, we have some height here of 6, but that 6 is changing, so we'll just call that height. And we also have some radius here, right, which is also changing as the water rises. And we also know that water is flowing into the tank at a rate of 9 cubic feet per minute. So that the dV dt is 9, positive 9, because it's increasing. So it seems like we should probably try to find the volume of this cone. Since we're given a dV dt, what's the volume of a cone? It should be 1/3 pi r squared h, right? And how can we relate r and h to each other to turn this into a single variable instead of multiple variables?
Since the ratio between like the main height and radius is like r equals h over 2, then it will probably be constant.
Yeah, these are similar triangles, right? They have in common a right angle, and they share this angle at the bottom in common. Angle, angle tells you triangle similarity. So the ratio from radius to height, 5 to 10, ought to be the same as the ratio from radius to height. And we are interested in how fast the water level is rising, which is a dH dt. So we probably want to get rid of the r and put everything in terms of h. So we could get that r is equal to h over 2. So we got volume equals 1/3 pi h over 2 squared times h, or volume equals 1/3 pi, or not 1/3, but 1/12 pi h cubed. Good or no?
Great.
So our dv dt value, when we differentiate both sides with respect to t, the left is dv dt, the right becomes 3/12 or 1/4 pi h squared times dh dt. And we want to know what dh dt is when the height is 6 and the water is 6 feet deep. So we'll go in and say dv dt is 1/4 of pi times 6 squared times dh dt. And we have dv dt. I don't know why I wrote dv dt again. What's dv dt? Is given to us in the problem, right? Should be 9. And what does that give us for dh dt when we simplify? Multiply by the 4 is 36 equals 36 pi. So dh dt ought to just be 1/pi.
Feet per
What
minute.
was it? Feet per minute? Is that where our units work? Yeah. Good or not? Cool. So you've got some optimization related rate problems to work on, about 20 or so of them, of which 10 are going to need to be turned in. There is just a few things to keep in mind when you're doing these. Most of the time, the formula that you're going to be, or what you might need to use to convert everything into one variable is similar triangles often show up, right? Similar triangles often shows up for that. Or use the volume or the surface area of whatever figure that you've got to try and figure it out to relate the two. Look at using the Pythagorean Theorem often, look at using your trig functions, that kind of stuff to write out your equations. And you should hopefully be all right with these. Any questions on anything? All right, I guess that's it for today.